Hey everybody, welcome back. I'm excited to go over this PowerPoint with you guys. It is the quantum model of the atom, part one, electrons as waves. So we think of electrons as being particles, and that is very much true. They have a mass. They are a little subatomic particle, but we're going to discuss them in this PowerPoint as being a wave. So I don't want to give it away just yet. I want to go through here. I want to explain a little bit about a little bit of these things to you, show you some things. This PowerPoint's going to be multiple videos, but just a little introductory. Let's get through some slides here. And yeah, let's kick it off. So looking at electrons, looking at electrons as a wave. So we are talking about quantized. Quantized is the word of the day. What does quantized mean? It means only a certain and specific amount. Take me, for example, if I were to walk up my staircase, I am only going up a certain and specific amount every single time. Every time I take a step up, I'm going up each step, probably about 6 to 7 inches. That is a certain and specific amount every single time. I can't just hang in the middle of the stair, right? There's nothing to step on. So when I go up the stair, I have to walk up every single time. That is what quantized is, a certain small specific amount. Think about when you're driving your vehicle, right? You step on the accelerator, you increase very nice, very continuously, very fluidly. Think about this. What if your car's accelerator was quantized? Then you'd be going, right? You get a lot of like whiplash because you're traveling at 5, then at 10. You jump right from 5 miles an hour right to 10. There is no 6, no 7, no 8, no 9. It's quantized. You're increasing by specific amounts every single time. So my fingerprint looks like that, but an element's fingerprint looks like this. And these are called emission spectrums, atomic emission spectrums. Now, you may be asking yourself, why on earth are we learning about this? Why on earth are we doing this? Mr. F, you got me talking about waves. You got me talking about electrons. Why are you talking about quantized energy? Or why are you talking about atomic emission spectrums? It's a very good point. Well, we need to understand what quantized is and what quantized amounts of energy are, because electrons only can exhibit quantized amounts of energy. And we need to understand that because we need to further our development of the atomic model. See, we started with Democritus, right? And it was just a sphere. And then we went to J.J. Thomson and we had the plum pudding model, and then Rutherford, and we had the planetary model. We still need to bring our model to the present. We still need to make adjustments to our model to better depict what an atom looks like. And we need to understand this, the atomic emission spectrum, before we can do that. So take a look at this. This is the atomic emission spectrum. Now, looking at this, we see that the very top, it almost looks like what you would see in class if I were to show you a poster of the electromagnetic spectrum and the visible light portion. It is a continuous rainbow. Rainbow? What's up, bro? No, rainbow. Now, yes, there are some black lines in there. I understand that. There is a little bit of some like blips. However, the majority of this is a continuous line spectrum. Now, if we go below that and we look at the next 4 examples, we see hydrogen is the first, helium, mercury, and then uranium. They are not continuous. Not continuous. Instead, they have lines in them. Take hydrogen, for example, the second one down. There are 4 lines. There's a red one at 656 nanometers, a blue one at 486 nanometers, a purple one at 434, and an indigo one at 410. Now, these lines are very bright. For that reason, we call those next 4, those 4 emission spectrums, we call them bright line spectrums, okay? Bright line spectrums. Now, these, I want you to think of these as a barcode. I want you to think of these as a fingerprint for an atom, for an element, for a compound. Whenever we see a gas, a hydrogen gas, it's going to have that bright line emission spectrum, okay? That's going to identify it. Helium, the third one down, it's always going to have that. Mercury is going to always look like that. And down at the very bottom, uranium will always have that spectra of lines. These are small, specific, quantized. These are small, specific amounts of energy that are being released that we could then see, that we could then record. Okay? Now, in order to view these atomic emission spectrum, what we do is we use something called a spectroscope. And what a spectroscope is it has a little eyepiece. So let me bring you guys to full screen. It has a little eyepiece shaped just like this. You would hold it like this. This is the business end. This is where you look through. This is the, I guess this is the viewing end. This is the business end. And on this end, I don't know if you can see, but there's a little slit. And that slit you line up with your light source. And then there is this, this open filter area. Now, when you look through that, when you look through here, and I'll show you guys in just a second, when you look through there, you're going to line, or I will line the light source up with the slit, and we are going to actually observe this side. And on this side, looking inside, you'll see numbers. You'll see 4, 5, 6, and 7. Now, those numbers correspond to the visible light spectrum. 4 is actually 400 nanometers, 5 is 500, 6, 600, 7, 700 nanometers. Those correspond to the visible light portion of the spectrum. And we will actually be able to see for any light source out there what its bright line emission spectrum is, or any element. So, if you guys can look through there, I'm actually taking this up, putting it right to the computer camera, and we could see, you'll see on the left-hand side of the screen, oopsies, there we go, that very bright white line, that is, I'm going to put my finger over it for a second, you see how it gets dim, right? That right there is where we're letting the light in. And then over on your left-hand side, you see the numbers. You can make out 4, 5, 6, and 7. Hopefully this is reflected when you're watching this, because I'm looking at this backwards. I apologize if this is backwards to you, but you do get the idea. And then you guys can almost make out some of those colors on the scale. We see a red line at about 600 and, let's see, 650. I want to say 650. We see, oops, lost it. There we go. We see a red line at 650, an orange line around 625, a green line at about 575, a blue line at about 5, and an indigo maybe, or a violet around 450. So that's what happens when you look through here. Now, I'm going to show you some other light sources, and I will explain to you what those are in just a second. So I will see you guys back in a little bit. All right, welcome back, everybody. We're going to use our spectroscope here and get some pictures or some video of some bright line and continuous spectrum. So hopefully you guys enjoy this. I'll explain to you what we're looking at as we go. So first thing we're going to look at is sunlight. So we're going to look right outside our window. We're going to line our spectroscope up right there, and we see that we have the light source coming in through that slit, and we actually have, I'm going to have to turn the brightness down. There we go. We have a continuous line spectrum. We can kind of see that over there. On the right-hand side, you see what appears to be a rainbow. And it goes throughout 4, 5, 6, and 7. The next thing that we will be looking at is an incandescent light bulb. So, let's adjust this brightness. And align that spectrum up with our incandescent light bulb. And we're going to notice, what do we have there? We have, again, we have another bright line spectrum. There we go. I apologize, guys, for the slip-shoddy type of video. going on here. All right, so I'm excited to show you guys this one. Here we have a electric source. It is plugged in to the outlet, and we have a little gas discharge tube inside. Now, inside this gas discharge tube, there is just air. The one that we have set up is argon gas, and when we set this up, we're going to see a nice little glow, so you guys can see that. We are essentially electrifying the gas inside, and that when it's electrified, the gas will release, and I don't want to give it away just yet exactly what's happening because I want you guys to figure it out, but it produces a light. This one that we're doing, you should be very familiar with this. This is neon, so all those cool neon signs you see, that's that, okay? We are just electrifying the gas, and if we now turn this on, we take our spectroscope and we line it up. Bear with me, guys. We line the spectroscope up. There is our color. We see over on the right-hand side, we see a bright line spectrum. I know it's kind of hard to see, guys, but hopefully you're getting the point. We see those bright lines there. It is not, I repeat, it is not a continuous spectrum. Let's do another one. Let's try, how about we try helium? So we're going to see what helium looks like in this case. Again, sorry for the slipshotty camera work, guys. Oh, it's kind of like a salmon color. So again, let's take our spectroscope, we'll line it up, and we will see what we have there. We see again, we have a bright line spectrum very clearly. There is a indigo one around 450, a blue around 5, green around 560, orange around 610, and a red around 6, maybe 45. Okay. We can identify with the use of a spectroscope what type of gas is in there. Now, the last thing I want to show you is one more light, and I'm sure you guys are familiar with this light right here. Okay, some of you have that one in your house. It's called a compact fluorescent. So what we're going to do is plug in, get this light source up and running. Whoa. We have our light source in. Let's take our spectroscope. And remember, the incandescent light bulb was a continuous spectrum. Let's see what this one is. Shocker, guys. Hopefully you're surprised. Maybe you're not. Maybe you knew. This is a bright line spectrum. You can see this one very bright. This is like the epitome of a bright line spectrum. That is because these are filled with mercury vapor. So you're looking at the bright line spectrum right there for mercury vapor. All right, guys, I hope you have enjoyed this little portion. I will join you guys back at the PowerPoint. All right, so hopefully you guys enjoyed seeing those bright line and continuous spectrums. So again, we can use that to identify what type of gas is in there. And so again, I'm sure you're asking me, what does this have to do with the diagram or the model of an atom? How is looking through a spectroscope going to help me, going to help you to figure out what an atom looks like? Well, these lines are being created by, all right, I'll just go and tell you. These lines are being created by electrons. And in order to understand how these lines are being created, we're going to have to understand how electrons operate. So that's the point of the next part, this next slide. We need someone who can make a connection between what we just observed, those bright line spectrums, and the model of an atom. And his name was Bohr, Niels Bohr. Him and I kind of look alike. What do you think? Anyway, Niels Bohr. And we're going to get into the Bohr model of the atom. But what Niels Bohr did was he took those bright line emission spectrums and he took what he knew from the planetary model of the atom, from Rutherford's model of the atom. That model, oops, you can't really see it, but that model right over there. And he connected them. One more slide and we're done with this video. Bohr said that when an atom absorbs energy, when it's being electrified. So think about what we just saw, right? We sent electricity into that gas. We electrified the atoms. We electrified the gas. Well, when an atom gets electrified, its electron will jump to a higher energy level. Now, even when you guys jump, you jump and then you fall right back down. The same thing with an electron. The electron gets electrified, it jumps up. It can't stay up there forever, so it has to fall back down. And when it falls back down, it emits electricity. It emits energy. It doesn't emit electricity, but it emits energy. And the way we observe that energy being released is through color. So the color we see, those lines, is the electron falling back down, releasing its energy, right? Because when you jump up, can't stay up there forever, you fall back down. Same thing with an electron. It gets electrified, it gets energized, it jumps up, and now it falls back down and releases the energy. Very important here, when it releases the energy, it's releasing an energy, it's releasing its energy in the form of a photon, P-H-O-T-O-N, a photon of light. That's a light particle. Now, how far that electron falls, that will correspond to the color that's released. If it falls a great distance, it's going to be a higher energy, more violet and blue. If it falls a smaller distance, that's a smaller amount of energy, more red, orange. And don't forget, this relates to our Planck's constant equation, E equals HF. So I hope you guys have enjoyed this video. I'm going to throw in a second video up there to continue going through this, and we'll get a little bit more in depth as to what the electron is actually doing. Please don't forget that word quantized, small specific amount. Don't forget photons are light particles, and the bright line spectrum is how we identify elements, and also we're viewing the electron falling back down and releasing light. So everyone have a great day. I will see you on the next video. Take care, everybody. Bye-bye. Bye, everyone.